In this video, I'll walk you through the detailed CAM processes involved in creating an aluminum mold for injection molding designed for your race car model. This project integrates several manufacturing processes, CAM programming, and machining operations to produce a precise aluminum mold for injection molding. I'll guide you step by step through the process of setting up your tool paths, choosing the right speeds and feeds, and preparing your stock on the Tormox for machining your molds. We'll be providing your team with the aluminum already pre-squared, ready to be machined. To begin, let's quickly discuss the critical constraints for a wheel CAD design. The wheel must not exceed half an inch in width and should have a maximum diameter of 1.125 inches, or 1 1/8 inches. Additionally, every feature must include radii equal to or larger than a 1/16 of an inch to ensure manufacturability, or 0.0625 inches. Next, we'll create two blank squares representing each half the aluminum mold. Using the combine tool in Fusion 360 to cut into the squares, creating negative impressions for injection molding, we'll be using this feature primarily to conserve our CAD throughout the process. Any changes upstream in the timeline in Fusion 360 will propagate forwards in time. Skipping ahead, you'll be in charge of designing the rest of the features pictured here. Starting off with the injection nozzle hole, a 45-degree angle hole for the injection molder nozzle, an air vent at the bottom of the wheel for air evacuation at a maximum of 0.003 of an inch depth to prevent any defects, and adding these pry cavities to easily separate the mold using screwdrivers after you've injected the plastic into your mold. We also included these locator pins, which will help align the molds accurately. These holes are drilled with a number 30 drill bit to ensure the mold halves remain accurately aligned when pressed together. Mold accuracy and surface finish are also crucial, so we must be extra careful with our tool paths and setup. I'll talk more about this later in the video. First, let's set up our CAM environment in Fusion 360. The same principles apply to most modern CAM software. However, I recommend Fusion 360 for its ease of use. I definitely recommend you stay within Fusion 360 when designing your molds in case you need to make any changes. I'll assume the front and back molds are ready at this point. In Fusion 360, switch to the manufacturer workspace. We'll click the drop down and switch from design to manufacture. We'll then click setup, new setup, and select the front or back mold to start. You'll get a new pane on the right hand side. Now I'll skip selecting a specific machine since Fusion 360 can generate toolpaths without that detail at this stage, but we'll make sure we're on the milling tab. And so moving on, we want to make sure that we set our work coordinate system correctly. Consider the initial orientation and position of the mold in the vise to help plan operations and avoid potential collisions. This is how the model will sit inside the vise, and I have a small render of what that will look like in real life. Now you don't have to model it like this, and this is meant to give you an idea of the tight tolerances you'll need to aim for. Align the WCS, or work coordinate system, to a logical reference. For example, the top left corner will make it easy for us to edge find, just like in Intro to Machining. For your orientation, make sure you choose Z-axis/plane and X-axis. This makes it easy to choose a line on your model for your X-axis and for your Z-axis, and reverse or flip if necessary. And stock box point as your selection method. Ensure the X-axis points to the right when looking at it from the top view, the Z-axis points upward away from the mold, and the Y-axis points away from you. This is how the model will sit inside the vise. You'll want to edge find on this face and on the back face. Let's go back to our model and make sure the orientation is correct. Now we'll choose our stock dimensions. We'll move over to the next tab. We'll choose fixed size box since we know the dimensions of our squared blank. And again, those dimensions are 1.875 inches by 1.875 inches in the XY plane and 0.5 inches in the Z. Enter these values in the corresponding fields. Okay, and our setup is done. Next, let's discuss our tool choices. Our job uses a maximum feed rate of 80 inches per minute and a spindle speed of up to 10,000 RPM, so we'll need tooling that can handle those kinds of feeds and speeds. Tool 1 will be our 1/8 inch ball end mill, ideal for both roughing and finishing, which go hand in hand with operations 1, 2, 3, 4, and 5. After operation 5, we'll move on to tool 2, the 1/16 inch ball end mill, selected for finer finishing details, operations 6 through 7, and tool 3, the number 1 center drill, used for pilot center drilling, operation 8, and tool 4, the number 30 drill, used for final drilling to full depth. Now, as a quick reference, this is how our setup will look like at the very end of our CAM process, and I'll go over these individually in detail. Let's go through all of our operations one by one. So we've already made our setup, but we're not going to make a new tree of operations. What I'll do is I'll go over every one of these operations that I already have. Now, because this is a 3D contour, meaning the contour changes both in the XY plane and in the Z plane, and this would be a little bit more obvious if I split the model in half. You can see in Z it also changes. Now our first operation is the adaptive operation, which you can find when you click 3D and adaptive clearing here. When you first open up the operation, and I'll close this analysis so I can have the full model here, you'll be greeted with a window on the right hand side. And most of these feeds and speeds are going to be the default values, which will change later. But for the time being, we'll want to select our tool. Now, right now, I have tool number 1, the 1/8 inch ball end mill selected, but for you, it'll probably be blank. So we'll click select and we'll get a new window pop up. Now, you'll probably won't have any tools loaded up at all. So we'll want to go over to the Fusion library. For some, you might actually have no tools available to you. So at the very bottom, there should be a blue button saying turn all libraries on, and then you'll be greeted with this giant list of tools. We'll make sure that in our tool category, the milling option is selected, and we'll go ahead and hit ball end mill to filter our results. And here we go. We have an 1/8 inch ball end mill that we can select from. Now I won't select it because I've already selected my tool. If you're working on Tormach 4, you can have flood coolant enabled. If you're working on any of the other Tormachs, make sure that this is disabled. Now, like I said, I'll go over feeds and speeds later, but you can also copy these parameters now if you'd like. Moving on to the next tab, I'm not going to have multi-axis tool orientation enabled, so don't worry about that. The next tab after that is the most important one. And this is how we'll select our geometry, or select what part of our model we want to actually remove material from our stock. Now we're starting with the main wheel mold impression. So for machining boundary, I'll want to have selection enabled. And then we want to use a chain method to select our geometry. Now, if you hover over any of these options, you'll get a hint box and it will tell you exactly what it does. But we want to go ahead and select chain. You'll get a new menu pop up, and then we'll want to select all of these top contours on the very top, including even these fillets that we have designed in. We'll go ahead and click OK. Now, one thing to check for is this little arrow, and this little arrow will dictate where the end mill is going to operate. Now, this arrow is on the inside of this contour, so the end mill will operate inside of this contour. If I click reverse, it'll actually put the arrow on the outside, and we don't want that. So I'll leave this unchecked, and we'll press OK. The next thing that we also want to make sure is that our tool containment is tool center on boundary. And I can open this up so that you can actually see the entire word. What this means is that our tool is not going to go beyond our boundary that we have. The center of the end mill is going to be on the boundary, but it won't go past that. This is pretty much default. I don't have the model selected. Our setup has already selected that for us, and the rest is default, so I won't be touching that. Next, I'll go over to my heights menu, and I think most of this is also default. But in some areas of the operations, I'll be messing around with the heights. The next most important tab is the passes tab. And this is how we'll dictate how much of a cut our end mill is going to take. So how far stepping over laterally and how far deep we'll be taking a cut. For our tolerances, we will want to make sure that all of our tolerances on all of our operations are 0.0004. And basically what this means is how Fusion approximates curved edges. The smaller the tolerance, the more accurate that curved edge is going to be, but the larger your file is also going to be. But we're not going to worry about file size at the moment. Our optimal load we want to keep at 0.0875 inches, meaning that our end mill is going to take 87.5 thou byte every pass. And that's step over, so that would be both sideways and also depth of cut. The next thing that we want to set is our maximum roughing step down, which is 0.0375. And our fine step down is 10% of that, so 0.00375. Don't worry about the specifics of this. just copy down these parameters. Next thing that we'll want to do is we'll want to leave stock to leave checked. And we want to leave 10 thou in each of the radial and axial directions. Now, stock to leave is going to leave a little bit of stock left over from this operation so that when we come back in later with a finishing pass, we can take that last bit off. And this will leave our piece very smooth. We'll also want to turn on smoothing. And same thing, we'll match our tolerance value at the very top. And if we click OK, we should be able to see a finished tool path. This might take a little bit of extra time just to load because it is a very large toolpath. Now that the toolpath has loaded, we can see exactly where those toolpaths are. The blue represents a cut. The yellow represents a move where the tool is moving from place to place. Now the red is a ramp, and basically what that means is how the tool is going to enter the stock. Now this is a spiral ramp, so it'll enter very gently into the stock before doing any larger cut. This looks good to me. Now you can see how the stock to leave is modeled on the piece of stock that we have. You can see a little bit left over here, but we'll come back in and clean that up. And that's how we'll remove the bulk of our material. Now if I go back into edit, I'll just quickly explain our speeds and feeds. Now these speeds and feeds I've found by trial and error, but for the most part, because we want to remove a lot of material in a relatively quick manner, we want to spin the spindle as fast as we can. And all of our Tormachs are capable of spinning at 10,000 RPM. So we'll leave 10,000 RPM. We'll also want to select our cutting feed rate. Now, I usually go by feed per tooth, which means how much of a cut each of our flutes is going to take. And I set this at 2 thou per tooth. This will automatically set our cutting feed rate. So notice that when I change this to 3 thou per teeth, which is a bigger bite, it'll actually increase my cutting feed rate as well. But I'll leave this at 2 thou per tooth. The next thing that I want to make sure I set is my ramp feed rate. Now, just like our feed per tooth for our cutting feed rate, I'll set the plunge feed per revolution or a ramp feed rate. So just make sure that you have this matched. And that should be it for our first operation. We'll click OK. And over here on the bottom right hand side, you can see how long this operation should take. And this should take about 5 minutes and 17 seconds. Now, if you don't have 5 minutes and 17 seconds, that might mean because you have a slightly different wheel design or that some of your parameters are not optimized. So it could go either way. In any case, we'll be checking over this when you come in with your G codes for final checks. Okay, moving on. We're going to continue with our tool number 1, our 1/8 inch end mill, but we're going to move on to a scallop, which is a little bit different from our adaptive cut, where this one takes equally spaced cuts all the way around. And this is how we're going to remove that last bit of material, that stock to leave that we left behind last time. And again, we'll find this in the 3D drop-down menu under scallop. But like I said, we're not going to do another operation. I'll just take a look at our current operation that I have here. Likewise, you want to select your 1/8 inch ball end mill. The same spindle speeds, although this is a significantly slower operation at 20 inches per minute, or at 1/2 thou per tooth. Same thing for plunge feed per revolution. Because we're not plunging in anymore, we can do this a little bit faster. So 4 thou per tooth is fine. For geometry, it's going to also be a little bit different. I'll be using face contours instead of a chain. And here I have 4 faces selected. Now, the 4 faces that I've selected are these fillets and this flat surface at the very end. So I can click all of these individually, and I should have my selection of 4 faces here. Just make sure that you have Start Inside enabled as well. We'll click OK. And again, we want to make sure that our tool is inside boundary. And go ahead and enable Contact Point Boundary and Contact Only. I won't really explain these, but you can figure these out just by the hint boxes. Again, everything else is going to be default. Our heights also default. Our passes, we're going to match our tolerance that we had left. We will also want to make sure that we're using outside to in, which basically it's going to start on the outside and it'll move inwards. This is pretty important because of the way ball end mills work. Ball end mills are better at cutting on the outside of the end mill rather than on the bottom, where the bottom is non-rotating. Our step over is going to be 10 thou, and we'll go ahead and select one way and keep up-down milling to both. Our smoothing, again, is going to match our tolerance, and we'll want to turn on feed optimization. Again, the defaults are fine here. And we'll click OK. and this should develop this tool path. Now this is a nice and controlled tool path, which is going to remove that last bit of material like I said before. And that should be the end for machining the interior part of our mold, or the actual part of the mold that's actually the mold. Next, what we'll want to do is we'll want to start cutting away at the inlet. Again, we're still using tool 1, and this is a very quick operation. This only takes 15 seconds for my design. Again, select your tool and copy down these feeds and speeds for your operation. For the geometry, that's going to be a little bit different from the rest. For our face contours, I'll want to select these faces, or at least where the 1/8 inch ball end mill is able to reach into. Again, dependent on how your design is. And we'll want to make sure that we start inside. Again, we want tool center on boundary, contact point boundary, and contact only enabled. Boundary overlap default parameters are okay. Now the only thing that we want to change is under the avoid machine surfaces tab. Here we'll want to select a second group of faces that we want to avoid machining. Now this is important so that we don't damage any of these areas while we're machining. So go ahead and click the plus icon, and you should get this little menu pop up. We'll want to select these 4 faces. 1, 2, 3, and 4. Again, all dependent on your design. The rest of the faces we don't really care about because we're not even reaching them because they're way beyond our boundaries. And we'll want to make sure that we click avoid surface. And we'll click OK. That'll turn these faces red. And so that way the machine knows not to touch these faces at all. On the heights menu, we'll want to do something a little bit different here for the bottom height. Now, because this piece, which normally would be like this in the vise if you were looking at it from the front part of the machine, with our Y pointing to the back, we know that this is going to be very close to that back jaw. So what I want to do is I want to set a bottom height that is no less than this bottom contour. Now these icons, which is a new update in Fusion 360, might be a little bit confusing, but because I know the diameter of this in my design, I can select an offset, making this the very bottom of this contour, the bottommost height. And this is the height where the end mill cannot go past. Moving on, we'll go into the passes tab. And again, very similar to our last scallop. In this case, we want to leave a little bit stock to leave. 10 thou is fine in both directions, and smoothing is also enabled. And we'll click OK. This will generate a tool path that looks like this. Now, the reason why we wanted a bottom height of the bottom of this contour is so that these tool paths go no further than this contour. And you can see in blue where these tool paths end, which is what we want. And this is how much material it's going to remove away, or it's capable of removing away with the 1/8 inch end mill. We need a smaller tool to get into these areas, which we'll do later. But for now, since we still have tool 1 in the spindle, we'll continue with the rest of the operations. Moving on to the pry cavities, we'll continue using the 1/8 inch end mill, and we'll use a new cutting strategy, parallel, which again, you'll find under the 3D menu. Now parallel is a little bit different. Again, select your 1/8 inch ball end mill and use these feeds and speeds parameters. Under the geometry tab, we'll use a closed chain and we'll select this outer chain here. Again, you may not see that right away, so we'll go ahead and hit selection under machining boundary. And we'll want to contain our tool center on the boundary. But what I've found during my machining operations is that it doesn't necessarily obey that. So I'll add in an additional offset of -5 thou, just to contain it a little bit better. Now this may be a little bit different depending on your design, but don't worry. We'll go ahead and make sure that both these options are also enabled. And again, for our groups of avoid machine surfaces, we'll want to make sure that we're avoiding these 2 faces. We'll click OK. Moving on to the heights tab, default is still OK, and the passes tab. So we'll want to make sure that our tolerance matches the rest of our operations. Our pass direction is also important here. For now, for our first parallel, the orientation is okay, although I think I'd switch the orientation on the second one, but we'll worry about that later. You can go ahead and copy these parameters. My pass direction is 0 degrees. Now what this will do is we'll change the direction of how your end mill is cutting into the stock. If, for example, I did 90 degrees, it'll change the direction. Now, we don't really want that. We want to make sure that it's cutting into the stock rather than in line with the stock. I'll go ahead and set this back to 0. And again, our step over of 10 thou is fine. I believe it'll also calculate this for you, so don't worry about that. Make sure that one way is enabled and both is enabled for up-down milling. Now, because by default, it'll want to cut into this cavity in one go, I'll go ahead and select multiple depths. And that way I can split up the passes into 2 layers. Our maximum step down should be okay with 30 thou, and then make sure that it's ordered by depth. We'll press OK. And that's the first pry cavity. Now we're going to do the same exact thing on the other side. And what you can do is you can actually duplicate operations. You can right click on your operation and then hit duplicate. Now when you do that, the only thing that we'll have to change is the actual geometry selection, the avoid machining surfaces. Make sure that these 2 faces are now the ones that we have selected. And that the pass direction is also matching with what we want, where it's cutting into the stock, not in line with the stock, or out of the stock. We'll want to make sure that our lead-ins are into. So again, our tolerance, same thing as all of our operations. And then we can just copy these parameters. So again, just like our other parallel operation, but this time with our pass direction at 180 degrees. Now again, this is all dependent on how you select your geometry. We'll click OK. And that should be it for all the operations with the 1/8 inch ball end mill. Next, we'll load in our 16th inch ball end mill. So with another scallop operation, we'll want to clean up our inlet. So for our tool, we'll go ahead and hit select. And again, under Fusion Library and ball end mill, we'll go ahead and select the 16th inch ball end mill. And these are the feeds and speeds that I want you guys to do. Again, flood cooling only on Tormach 4. So for our geometry tab, we have again selection enabled and our face contours enabled as well. And these are the faces that I want you to select. So tool center on boundary, contact point boundary, contact only, and then our avoid machine surfaces that I want you to select as well. Our heights tab, again, I want you to follow this where our bottom height is going to be the very bottom of this contour so that we don't go past it. And in our passes, our step over is going to be even smaller now at 5 thou. This will make sure that we have a very nice surface finish at the very end, meaning that our surface is nice and smooth for the plastic to flow over. Again, one way, both, and smoothing turned on. And make sure that outside in is enabled, okay? And this is what it should look like. This will come in and clean up that last bit of stock that we left behind. And then finally, our last scallop operation. And this is what's going to create our vent. Now the vent is a very shallow vent at only 3 thou from this surface down to this surface. And notice that I have these fillets on the sides. This will match the fillet radius of our end mill. I believe my radius is 0.0313. Indeed, half the radius of my 16th inch ball end mill. And this is perfectly fine. So we'll go ahead and select tool number 2, 16th inch ball end mill. We'll copy these feeds and speeds. For our geometry, we'll select the entire contour all the way around using a face contour. And again, these are 5 faces, selecting both the fillet radius and the bottom flat surface. Now, for this one, I'll want to avoid enabling contact point boundary. This is not going to help us here. Again, avoid machine surfaces. We'll want to avoid these areas to the side. And in passes, we want to make sure our tolerance is good. Our step over at 5 thou, our direction one way, our up-down milling both, smoothing and feed optimization turned on, and go ahead and click OK. Now that will be all of the end milling operations. The only thing that's left to do is drill out these locator pins, and that should be very straightforward. We'll want to split it up into 2 operations. The first one, spot drilling, and the second one, the actual drilling. So to find our drilling operation, we'll go ahead and find it right up here under drilling. And then we'll want to find our center drill. Now I'm using a number 1 center drill, and we have plenty of those in the back of the office, which you can ask for. We'll go ahead and select. We'll go to Fusion Library. We want to make sure that we're on the hole making category. And then we want to go over to center drill. And here in parentheses, you can see the number 1 center drill. And go ahead and select that. Now we're going to be using slightly different speeds and feeds. Our spindle speed is going to be at 2000 RPM, and our plunge feed rate at 10 inches per minute. Moving on to the geometry, again, we can just select the 2 holes that we're going to be making, and everything by default is okay. Now for our heights. For our heights, the bottom height is the one that we want to make sure that it is set to chamfer width. And so this, by default, will calculate the diameter of the spot drill chamfer width. For cycle, we'll want to make sure that drilling rapid out is enabled, and we'll click OK. And this is a very fast operation, 7 seconds. Next, for deep drilling, we'll want to select the number 30 drill. So we'll go over to our Fusion library again, drill, and then we'll want to scroll down until we find the number 30 drill. And go ahead and select that. Our spindle speed is going to be at 2000 RPM, and our plunge feed rate at 10 inches per minute. Moving on to the geometry tab, again, the 2 holes. Our heights, we'll want to make sure that our whole bottom is selected for the bottom height. And we can add in a further offset from the actual model depth. Now I believe the model depth is at 0.125. We'll want to go just a little bit deeper than that, at 0.015 inches. And for our cycle, we want to do deep drilling full retract. Our pecking depth is going to be set 40 thou, or 0.04 inches. Our minimum pecking depth is going to be the same. And if you hover over every field, you can see exactly what that means. And we'll click OK. And that's it. That's the entire front mold fully cammed. You can go ahead now and select all of them and simulate. And you can see the entire simulation, one operation at a time. Now this first operation is going to take a while, but you can skip to the next operation. Sometimes it'll take a little bit of while to load the stock that's being removed, and then it goes on to the next operation, which is the finishing pass. Now I can pause it, I can go slower, I can see how much material that tool is actually removing. Now this is only possible because I've made my tool transparent. I've also set my stock colorization to comparison. And basically what this does is I can see in blue where there's still stock left to be machined. Green is the stock that's already been to tolerance, and red is going to be where our stock is below tolerance, although I don't see any here. You can also make sure that shaft is only enabled. That way you don't have the giant tool holder in the way. And I've set the mode for the tool path to be tail. That way I don't see all tool paths at the same time. And we can go ahead and hit exit simulation after you verify that there are no errors. Once you've verified that our tool is not going to collide with our stock, now you can simulate one operation at a time if you right click on it and also hit simulate. Or you can select the entire setup and hit simulate to see the entire operation list. Plenty of coolant will be required for these operations. High velocity coolant or an air blast is essential for aluminum machining to clear chips efficiently. We don't want those chips piling up where the tool is cutting, otherwise that may lead to a break. That could also increase the heat generated by the tool as it's cutting. We'll also want to avoid that. Using high-speed adaptive clearing not only maintains constant tool load, but also enables faster speeds and feeds, significantly reducing cutting cycle times. That is why we're maxing out the RPM on the Tormachs and running them significantly faster than what's on the charts. Though caution is always a must when running things faster. Now let's talk about work holding. A proper fixture is essential for achieving consistent, repeatable results, especially when precision is key in mold making. A standard machine vise works well for small molds, just like the vices we have on all the Tormachs. And make sure that we're using the 1 1/8 inch parallels like I have here. We also want to avoid over tightening, which can distort the aluminum stock. Whenever you start feeling resistance when you're tightening, go about 1/8 of a turn. That'll be more than enough pressure to hold your piece. And finally, we can pat it down with the dead blow hammers. And we can even use a little piece of wood to make sure we don't damage our stock. And this is your final piece after all operations have completed, minus the engraving, of course. Remember that you can always come to us to ask questions and your TAs, so don't hesitate. And happy machining.